Hello everyone and welcome to DCF 255 Week 5 Lecture 5, the Internet Layer. In this week's lecture, what we want to discuss is the Internet Layer functions, the dual stack environment, IPv4/v6, IPv4 addressing, IPv4 changes to preserve the address space, IPv6 addressing, tunneling, scoped addresses, IPv6 from a programming perspective, user interface design, IP family independence, and determining IP family before creating socket. So first things first, let's take a look at the functions of the Internet layer. The following functions, as you can see, first, the Internet layer accepts all the content from the transport layer as data. It is responsible for adding header containing the source and destination IP addresses. It is responsible for making routing decisions to decide the best route and for a smooth transition to IPv6, which commenced in 2012. All new hardware must be dual protocol stack enabled, called IPv4/v6. In this slide, what we examine is how IPv4 addressing is taking place. In classful addressing, IPv4 addresses are divided into 5 classes, namely A, B, C, D, and E. Each class has a fixed number of blocks, and each block has a fixed number of hosts. So class A begins with a 0 in its first octet, which is the first byte. The remaining 7 bits gives a maximum of 127 addresses. So 2 raised to the power of 7 gives us 127. And therefore the range of addresses in class A is 0 to 127. In class B, the first byte begins with a 10. The remaining 6 bits give maximum addresses of 64. So 2 raised to the power of 6 will give you 64. And the range of addresses in class B is 128 to 191. Class C begins with a 110 in its first byte. The remaining 5 bits gives a maximum of 32 bits, which is 2 raised to the power of 5 gives us 32. And the range of addresses in class C is 192 to 223. Class D begins with 1110 in the first byte, and the remaining 4 bits gives a maximum of 16 addresses, 2 raised to the power of 4. And the range of addresses in class D is 224 to 239. So what we understand from this slide is the other information about what we need to understand is the subnet masks. So IPv4 addresses are 32-bit long binary addresses. So in this example, for example, we have 145.10.34.3. Each of the decimal numbers, when converted into binary, translates into 8-bit binary number. And that's how you get your 32-bit long binary address. The subnet mask, let's understand what the function of a subnet mask is. The function of a subnet mask is to divide an IP address into 2 parts. One part identifies the host, which is the computer, and the other part identifies the network in which it belongs. So you can see in this diagram that you get your host and you get your network. So you've got your prefix and your suffix bits that we'll talk about in a second. In class A, so the way it actually goes about doing this distinction between the network part and the host part is by using a what we refer to as the uh, bitwise AND operation between the IP address and its subnet mask. So in class A, the subnet mask is 255.0.0.0. 255 is basically ones, 8 ones when converted into binary. And in insider notation, it will be represented with a/8. In class B, the subnet mask is 255.255.2.0.0, which is 16 ones when converted into binary. And in insider notation, you would see this as a/16. In class C, the subnet mask is 255.255.255.0. And so the first, second, and the third octets add up to 24 ones when converted into binary. And in insider notation, we would represent that as a/24. So with IPv4 address space, which we are familiar with, for example, in address such as 192.168.0.1, it is based on 4 octets or 32-bit addresses, as we mentioned. So each octet range values from 0 to 255. Thus, the maximum size of the address space is 256 times 256 times 256 times 256, which translates into, when you do the math, you get 4.3 billion addresses. Now, this sounds like a big number. The 32-bit addresses can be divided into different classes to allocate network and host addresses. However, with the development of the World Wide Web and the growth of PCs, use of smartphones, tablets, gaming systems, and voice over IP systems, far more IP addresses became necessary than the founders had anticipated. So a new address space, IPv6, was introduced, and that uses 128-bit addresses, and it is capable of 340 trillion addresses. So with the depletion of IPv4 addresses, which was predicted in 1993, steps were taken to preserve the space as long as possible. The IETF instituted the following changes. Private address spaces are created to allow networks to create LAN addresses with the approval of the Internet Registry. However, the hosts on the LAN cannot communicate with public Internet addresses except through a proxy gateway. NAT, or Network Address Translator, was created to act as a proxy gateway which converts private host addresses to public addresses to access the Internet. This makes it possible for many LAN hosts which can share a single Internet address. DHCP, or Dynamic Host Configuration Protocols, was created to act as a server to allocate addresses from a pool of available LAN addresses. The address assigned to the host is leased from the server for a specific period of time, and it can be reallocated to another host when the lease expires. Thus, many hosts can share a pool of addresses. CIDR, what we saw in the previous slide, is classless inter-domain routing, was a fundamental change in how IP addresses were assigned. The old class-based system of allocating IPv4 addresses was discontinued for a classless system which used 32-bit address space more efficiently, avoiding wastage of IP addresses. All of these network technologies we have heard before are currently implemented in our home and in Seneca networks. In North America, IPv4 will continue to be used for a long time. Networks won't convert to IPv6 until new hardware is required. Let's talk about IPv6 addressing. IPv6 addresses you are of three different types. There's the unicast, the multicast, and the anycast. Unicast is a one-to-one address. Packets sent to a unicast address travel between two hosts on a single interface. A multicast address is a one-to-many address. Packets are sent to multicast address travels to all interfaces identified by the multicast group address. This replaces the broadcast address used in IPv4. Anycast address is a one-to-one address and is sent to the nearest host. Packets sent to Anycast address are sent to a single interface of the nearest host identified by the address. So let's take a look at this particular slide. What we see over here is the IPv4 and IPv6 we can see that they are connectionless protocols. What that means is that every data packet that is sent across the network is treated as an independent unit. IP does not maintain the details of the connection between the server and the client and does not guarantee reliable delivery. It is a best effort delivery system trying to avert data loss as much as possible. If the host is located on the same network, this is called local delivery. And if the host is on a different network, it is called remote delivery. With remote delivery, the data will be handled by intermediate devices called routers, which will forward the data based on the destination address. The sender is unaware of how the data is transmitted to the destination. This is similar to when you mail a letter. You put in the address on the letter, and you're not aware of the number of intermediate steps that Canada Post will use to forward the letter to its destination. ICMP. IP works with ICMP, which is the Internet Control Message Protocol. ICMP is responsible for generating error messages when an error occurs during data transmission. The transport layer protocols, namely TCP and UDP, decide to retransmit data based on the error message that is received. In the table, we see the comparison between IPv4 and IPv6 layers and the protocol specifications of each layer. So when you ping a host, the message is an ICMP echo request packet, which the receiving host returns ICMP echo reply packet, or a host unreachable message if the host is offline. IGMP is Internet Group Management Protocol, and it is used for grouping multicast hosts. ARP is the Address Message Protocol, and it is used by IP to resolve MAC addresses of a host when the IP address is known. An ARP request packet is a broadcast to all hosts saying, whoever has this IP address, please send me your MAC address. The receiving host that has the particular IP address will then return a unicast ARP reply to the sending host so that the data link layer frame can be completed. IPv6 has new protocols but serve the same function. ICMP v6 is the error message protocol. MLD is the multicast listener discovery, which is an improvement version of IGMP, and it is used for multicasting and neighbor discovery, which replaces ARP. With IPv6, all devices can be connected to the public network. which will make it easier for users to manage home automation, file sharing, online gaming, etc., without complex settings on their routers. Dual stack approach to IPv6 means that IPv4 will be around for quite some time. IPv4 devices will continue to work in the foreseeable future. However, there are three reasons why businesses should plan to change to IPv6. The first one being inevitability. At some point in the future, IPv4 will no longer be supported. Moving to IPv6 when hardware needs to be changed is a good approach. Second one is efficiency. IPv6 is a better protocol than IPv4, with faster routing by removing the need to check packet integrity and fragment a packet. In IPv6, only the sending host performs fragmentation. If an IPv6 router cannot forward a packet because it is too large, the router sends an ICMP v6 packet too big message to the sending host and discards the packet. NAT will no longer be needed because each host will have a unique IP address on the public network, unless the network continues to use private addressing. The last one is security. IPv6 was built from ground up with the security in mind, with built-in encryption. In IPv6, what it does is it encrypts traffic and checks packet integrity to provide VPN-like protection for standard internet traffic. IPv6 has a network address of 48 bits, which is assigned by the Internet Society. So adjacent to the network bits are the network prefix bits, which businesses can use to divide their address space to match organizational needs. These bits use CIDR notation to determine which bits have fixed values and which bits represent the subnet identifier. The remaining 64 bits are the host bits. For IPv6, the 128-bit address is divided along 16-bit boundaries. Each 16-bit block is converted to a 4-digit hexadecimal number and is separated by colons. The resulting representation is known as colon hexadecimal. So as you can see in the figure, the 128-bit address is divided into 16-bit boundaries. Each 16-bit block is converted to a 4-digit hexadecimal number and separated by colons. The resulting representation is known as colon hexadecimal. IPv6 address in binary form is shown in this figure as well. So IPv6 representation, what it does in order for simplification, it removes the leading zeros from within each 16-bit block. So in order to achieve that, each block must have at least a single digit. So in this example, in our illustration, you can see that when you have two leading zeros in this block, they are removed. So you would end up with, in this first block, you have a 2-1-DA, and so that stays the same the way it is. In the next block, you have a 0-0, so that is removed because there is a single digit over here, or at least one digit over here, so that we can drop the two zeros. In the next block, you can remove the leading 3 zeros, but you do need to maintain that 1 0 over here, so that stays, followed by a colon, and then you continue on down this path for the remaining blocks, and you have the 2 zeros over here, but because you have you have an F over here in this particular block, so you can drop these 2 zeros. So since there is at least one single digit followed by two leading zeros in the last hex address, as so we can remove both the zeros can be removed. Okay. So the next thing is also from a simplification perspective. There is a method of compressing zeros that is also used. So some type of addresses contain long sequences of zeros, and to simplify its representation of IPv6 address, a contiguous sequence of 16-bit blocks set to 0 in the colon hexadecimal format can be compressed to a colon colon or a double colon, what is referred to as also known as a double colon. So, for example, the link local address FE80 colon 000, okay, colon 0 colon 0 colon 0, and then the rest of this address in this block can be simplified. Okay, so what we can do here is we can remove this block of zeros and replace it with a colon. All right. In this example over here, you have a whole bunch of a string of zeros in the block. Okay, so you can drop these zeros, but you have to put a colon in its place. So zero compression can be used to compress only a single contiguous series of 16-bit blocks expressed in colon hexadecimal notation. You cannot use zero compression to include part of the 16-bit block. So, for example, you cannot express FF02 colon 30 0000 colon 5 as a FF02 colon 3 colon 5. So you cannot do that. So to determine how many 0 bits are represented by the double colon, so that would be the inevitable question, is to say, well, I see the double colon, but how do I know how many 0 bits are represented in there? What you would do is you would count the number of blocks in the compression of the address, subtract this number from 8, and then multiply the result by 16. So, for example, the address FF02 colon 2 has two blocks, FF02 block and the 2 block. So the number of 0 bits expressed by the double colon is 96. How does that arrive? How do we arrive at 96? 96 is going to be equal to 8 minus 2 times 16. So you have 8 minus 2 in brackets, which gives us 6. 6 times 16 gives us 96. So zero compression can be used only once in a given address. Otherwise, you would not be able to determine the number of 0 bits represented by each double colon. Zero compression can be used to compress only a single contiguous series of 16 blocks expressed in a colon hexadecimal notation. You cannot use zero compression to include part of a 16-bit block. Let's talk about IPv6 prefix and dual environments. The 128 bits of the IPv6 address must denote the network address and the host address for packets to be correctly delivered. IPv6 uses CIDR notation to denote the number of bits used for the network. So within a network, all network hosts will have the same network prefix. The prefix is indicated as a / followed by the number of bits. So for example, you have 2001 colon CDBA colon 9ABC 5678 colon / 64, which denotes the network address. And the host address range from 2001 colon CDBA colon 9ABC colon 5678 colon and then a whole string of zeros all the way up to 2001, and then its range is going all the way to FFFF colon FFFF colon FFF all the way. So that is your network and your host representation from the IPv6 128-bit addresses. Okay. For dual environments, a specific notation is permitted. So as you can see in here, you have XXXXX, which represents the network portion, and the DDDD is your host representation. So the first 6 high order bits, 16-bit pieces, is basically 96 bits. So you have, looking at the syntax which we see in the slide, the X's are the hexadecimal values of the 6 high order 16-bit pieces, and the D's are the decimal values of the 4 low order 8-bit pieces of the address, which is your standard IPv4 address representation. And the prefix of that is a 96. So for example, IPv4 address 126.101.64.1 .64.1 would be stated as you see over here. So that would be : 126.101.64.1/96. There's only one exception to this rule, is that for the loopback address. The 127.0.0.1 is a loopback address to test if the TCP/IP is properly installed on the local machine. And this address has an IPv6 representation of : 1/128. So let's take a look at the IPv6 tunneling for dual environments. The dual stack approach is an important feature to ensure compatibility between IPv4 and IPv6 hosts. It is possible that packets arrive at the router that are not IPv6 enabled. And to solve this problem, a tunneling process provides the functionality for IPv6 over IPv4. Say, for example, you are at work and have a dual stack host, and you want to send a file to your home, which also has a dual stack. That's a non-issue. However, if the upstream ISP is not IPv6 enabled, you would ask, well, how is this file going to be sent? The internet layer of PCA will encapsulate the IPv6 address inside an IPv4 address, so the packet can travel over the ISP network, and then PCB's internet layer will de-encapsulate the address. Okay, so that is how the tunneling takes place. So how would a router or host know which protocol to use? So this takes us to the concept of the tunneling, where we talk about dual environments. So to determine which protocol to use, a router will use a DNS records. Users will communicate on the internet using fully qualified domain names, FQDN, not IP addresses. DNS records map the IP address to the domain name. So the transition from IPv4 to IPv6 from a user's point of view is seamless. For instance, assume that we have a dual stack and we want to access, say, the URL https www.senecacollege.ca. A dual stack node will behave as follows. If www.senecacollege.ca resolves to an IPv4 address, connect to the IPv4 address. In such case, the DNS database record for www.senecacollege.ca will be as follows. It will be www.senecacollege.ca.in A142.204.0.0, followed by followed by, say, if the Seneca College results to an IPv6 address, connect to the IPv6 address. So it will then be represented as www.senecacollege.ca in AAAA FE80 and colon DC 28 and colon FFFF colon 1234. So if senecacollege.ca resolves to multiple IPv4/v6 addresses, the IPv6 address will be tried first, and then the IPv4 addresses will be tried. So, for example, with the following DNS records, we will try connecting to FE80 DC28 FFFF 1234, then www senecacollege.ca INAAA FE80 DC28 FFFF 1234, followed by www.senecacollege.ca INAAA FE80 DC28 FFFF 5678, and then followed by www.senecacollege INA 142.204.0.0. Since we assume that IPv6 hosts will be able to use IPv4 as well, the internet will be filled with IPv4/v6 geostack devices for the near future until the use of IPv6 becomes dominant. So now what we need to understand is from a programming perspective, IPv6 from a programming perspective. From a programmer's perspective, IPv6 is very different than IPv4 programming and will represent some new challenges. The first one of the three considerations are the user interface design. The second one is the IP family independent and determining IP family before creating a socket. So let's take a look at each of these. From an IPv6 programming perspective, IPv4 addresses provided a rigid format. IPv6 addresses are less rigid because of the convention of using a double colon to provide a truncated address, such as 1010 can be written as 1004:1. This requires programmers to take this capacity into account when creating user interfaces which display the IPv6 address. Also, the text box must be capable of supporting the IPv6 address with the embedded IPv4 address, such as in the first block 0000:0000, 0000:000, at the end the IPv4, which is 10.0.10.1. So, and if the scope identifier is added to the address, the length could be increased by another 11 characters. So due to many factors such as length, complexity, and the significance of sections within the IPv6 address space, IPv6 is not conducive to modification or specification by users. Therefore, the need to provide users with the capability of specifying their own address is reduced. Additionally, due to the complexity associated with IPv6 addressing, providing administrators with the capability of specifying IPv6 address information is not likely to occur on a per node basis. Displaying an IPv6 address in the user interface design is not inconceivable, and therefore developers have to consider the variability in the size of the IPv6 address when modifying an application to support IPv6. And so what we want to consider is the difference between IPv4 address length predictability and IPv6 address length consideration. IPv4 addresses are predictable in size because they, of course, rigidly follow the dotted decimal notation, as the following address we have seen before, 10.10.256.1, for example. With the complexities of IPv6 format and the difficulty in associating it with a host, it is more likely that the user will rely on name-based notation rather than number-based notation. So it is predicted that with IPv6, DNS will play a greater role in dynamically allocating addresses, and in which case a text box in the user interface may not be necessary unless the application is an administrative program. So here are some of the topics a programmer has to consider. Should a number be based should number-based or a name-based notation be used? So that's the first thing. The second thing is, should the truncated address be used in the interface? The double colon is an optional method of notation to simplify the address, not a specification. So does the user need specific parts of the address, such as the subnet, prefix, scope identifier, or other fields? And lastly, if the user is to enter an IPv6 address as part of the URL, the address must be enclosed in square brackets to avoid ambiguity with the port number, which is also separated by a colon. So for example, http :// in square brackets f3 80 dc28 fff followed by two colons and a 1, close the square brackets, :80 for the port number, and /64. We could use a simple switch statement to determine the address of the address family and denote and handle it in dotted notation, decimal notation, or IPv6 and handle it in hexadecimal notation. Well, unfortunately, the answer is not as simple. Code, like the one we see, has to be avoided for the following reasons. Hard coding the address family has to be avoided because the application will not function unless the operating system supports the address family. So for the near future, there will be devices that are IPv4 specific, IPv6 specific, or IPv6/v4 dual stack. Hard coding the address will make interoperability difficult. So if, say, a new protocol is developed, applications which are family dependent will not need to be written. On the other hand, a family-dependent application will need to be changed. A device that is IPv4 specific will not know how to tunnel a IPv6 address inside of an IPv4 packet. Interoperability will be increased if family-independent structures and functions are used. To ensure IPv6 interoperability, review the IPv4 code base looking for inappropriate controls. If checking Unix applications, it is advisable to use grep to check for any specific functions, family-specific functions listed. Windows has also come up with a tool called checkv4.exe, available in the Microsoft SDK or available as a web download. When you run your code through the utility, it alerts you of any IPv4 specific data structures and function calls. Alternatively, you can search a code base for instances of the SOC address or SOC ADDR in structures and change all such usage and associated code as appropriate to the socket address, the SOC ADDR_storage structure. The APIs listed above should be avoided. So the following APIs that take struct in address to struct into underscore ADDR is recommended to be avoided. Another important reason for using SOC ADDR is due to the scoped IPv6 addresses. Unlike IPv4, where address was tied to host, IPv6 address is tied to an interface and a host, and it can have several interfaces. So the 128 bits does not uniquely identify the peer. In the diagram in here, we see that from PCB, we can see two hosts with FE80::1, one on Ethernet 1 segment and another one on the Ethernet segment 2. So you can see that that's the case. So to communicate with the host A or C, PCB has to distinguish between them with a link local address specifying the outgoing interface to use, called the link local address. 128-bit address is not enough. SOC ADDR in 6 has a member named SIN6 underscore scope underscore ID to disambiguate destinations between multiple scope zones. String representation of a scoped IPv6 address is augmented with a scope identifier after the percent sign, such as FE80::1 with the percent ether1. Okay. In IPv4 socket programming, the get address info and the get get address info and the get host by name are commonly used after the socket is created using the AF_INET address family. On dual stack hosts, this approach will not work because the address family of the host name is not known. Only then, so the address resolution using get address information function must be completed first to determine the IP address and the address family of the remote host. Then the socket function can be called to open a socket of the address family, and it returned by the get address information or get ADDR info. So this is a fundamental change in how socket applications are written, since many IPv4 applications tend to use different order of function calls. Also, if the name resolution returns both IPv4 and IPv6 addresses, then a separate IPv4 and IPv6 sockets must be used to connect to these destination address. If you're writing a Windows socket application, these complexities can be avoided using the new WSA connect by name function available on Windows Vista and later. The code that is in this example shows the proper sequence for performing name resolution first. So you want to perform, so this is, you can see in the 4th line in the source code, and then the opening of a socket in the 19th line. Okay, so you can see those two notes over there. And some of you might have identified this as a C++ code, which is correct. So in summary, what have we discussed today? The internet is responsible for determining the IP address of the remote host and adding the sending and receiving IP addresses to the header. As the message is forwarded to the receiving host, the internet layer makes the routing decisions. The depletion of IPv4 address space led to the creation of private addresses. CIDR, DHCP, and NAT technologies, which have been created, which have created the present network landscape. So, although IPv6 was launched in 2012, it is expected that IPv4 is going to be around for a long time in North America. Companies and should the change to IPv6 be better, is better for performance and security. And for a smooth transition to IPv6, it is mandated that all hardware be able to handle both the IPv4 and v6 dual environments. And these devices will be able to tunnel IPv6 addresses inside IPv4 addresses for IPv4 specific devices. IPv6 addresses are assigned to an interface and not the host. Therefore, there is a link to local address which allows 128 addresses to be assigned with a scope identified to avoid ambiguity. In IPv6, address space has three types of addressing: unicast, multicast, and anycast. The address space is 128 bits long and is in hexadecimal format. A number of techniques are allowed to simplify the address, as we saw in our slides earlier. The use of IPv6 has made fundamental changes in how programmers design user interfaces and write socket programs. Given the size and complexities of displaying IPv6 addresses, programmers must decide if they want to use a name-based system. Also, in writing programs, the socket address type must be determined before opening a socket. And that's all for this week's lecture. There's a lot of things that we have covered, but this material is going to be included in our test number 1, the midterm test coming up next week. So you want to review your notes and go through the lecture and understand all the details for next week's test. Have a wonderful day and remaining part of the Thanksgiving weekend. Take care. Bye.